Welcome to the video for Lecture 17, Section 2. This video goes over the unbalanced Wheatstone bridge circuits that are used to measure resistance changes in resistance temperature detectors and strain gauges. With unbalanced Wheatstone bridge circuit, we will measure V0 using a data logger or PDAC55 unit. The device needs to have a large resistance. By the end of this video, we will find out that V0 depends on the supply voltage, the number of active arms, and how the resistances of each arm change. Here is another sketch of a Wheatstone bridge circuit. This time, we label the resistances in terms of R plus delta R and R minus delta R. This corresponds to the way strain gauge resistances are commonly described. The resistances of arms 1 and 3 are R minus delta R, and the resistance of arms 2 and 4 are R plus delta R. This will mean later that we will want to mount strain gauges that are in pressure in arms 1 and 3, and the strain gauges that are in tension in arms 2 and 4. Wheatstone bridge circuit output voltage, V0, depends on the number of active arms. We will start our development for this case when we have one active arm. The active arm will be number 2. Using Kirchhoff's voltage law around the loop, including V0, V2, and V1, we get that V0 equals V2 minus V1. Then, by using the concept of voltage dividers again, which we used in the earlier video, we can write the voltage drop across R1 and R4. We can also write the equation that gives the voltage drop across R2 and R3. With the equations for V1 and V2, we can substitute them in the equation V0 equals V2 minus V1. It is very common to use matched resistors that have the same resistances, where R1 equals R3 equals R4, and therefore we can use R to replace R1, R3, and R4. After we make the substitutions, the expression for the output voltage V0 equals Vs times R2 over the sum of R2 and R minus 1/2. This simplifies the equation quite a bit. We are really interested in the change in resistance, so we will define R2 as R plus delta R as assuming that we have a single strain gauge in tension attached to arm 2. If we make the substitution and go through some algebraic manipulations, we get the expression for delta V0 as this first equation. The next step is to recognize that the resistance R is going to be much larger than delta R. Therefore, the change in the output voltage of our Wheatstone bridge circuit will be very close to Vs times delta R over 4 times R. Now we recognize that delta R over R is part of the gauge factor term. So we can write that it can be equal to epsilon times F, where epsilon is strain and F is the gauge factor. Then we get that the change in output voltage from our Wheatstone bridge circuit with one active arm is approximately equal to Vs times epsilon times the F divided by 4. This equation is the one that you want to highlight. You will not be expected to develop the relation between the strain and the Wheatstone bridge circuit output voltage. However, you are expected to use this equation when you have problem with one active arm. Next, we will assume that we have 2 active arms. This is called a half bridge because 2 out of 4 arms are active. For the development, we will assume that arms 2 and 3 are active. We will again use the equation that gives us the output voltage in terms of the supply voltage Vs and the 4 resistances. To make our lives easier, we will assume the resistances of arms 1 and 4 are the same and equal to R. Then we will say that the resistance for arm 2 is a strain gauge in tension and R2 equals R plus delta R. The resistance for arm 3 is a strain gauge in compression and R3 is equal to R minus delta R. After we make the substitutions and simplify the equation, we get that the change in the output voltage of a Wheatstone bridge circuit with 2 active arms with 1 strain gauge in tension and 1 in compression is approximately equal to Vs times epsilon times F divided by 2. Again, this is an equation that you will use in half bridges with 2 active arms. This slide shows how 2 strain gauges that are part of a half Wheatstone bridge circuit need to be mounted on a cantilevered beam that has a downward load acting on the end of the beam. Arms 2 and 3 are active and arms 1 and 4 are not active. They will have a constant resistance R. The strain gauge on top, R3, will be in tension, so the resistance will increase to it is R plus delta R. The strain gauge on the bottom, R2, will be in compression, so the resistance will decrease and be R minus delta R. These match the variables we used in the development of the equation for half-bridge Wheatstone bridge circuits with 2 active arms. Wheatstone bridge circuits have 4 arms, and we can make all 4 arms active. When all 4 Wheatstone bridge circuit arms are active, it is called a full bridge. Similarly to what we did with half bridge, we will need to specify where and how the strain gauges are mounted to get the most output possible with a full Wheatstone bridge circuit. Strain gauges 1 and 3 will be mounted in compression on the bottom of the cantilever beam. Strain gauges 2 and 4 are mounted on top of the cantilever beam in tension. The load is downward. When we have 4 active arms, the output voltage delta V0 is approximately the product of V times Vs times F times epsilon. These 3 expressions can be generalized. The output voltage delta V0 is approximately the product of Vs times F times epsilon times N over 4, where N is the number of active arms. When N equals 1, you get the expression for a quarters Wheatstone bridge circuit. When N equals 2, you get the expression for a half Wheatstone bridge circuit. What we really want to find is the strain given the Wheatstone bridge circuit output voltage delta V0. The equation is shown here. The strain in microstrain is equal to 4 times delta V0 divided by Vs, F, and the number of the active arms. All of the previous examples showed how to mount the strain gauges on a cantilever beam. There are other configurations with which 4 strain gauges can be mounted. This slide shows how to mount 4 strain gauge on a beam in axial loading. Compression loading is shown here. The mounting works for tension loading too. This is called an axially loaded beam using a Poisson arrangement. This arrangement is used in some load cells. 2 gauges, 1 and 3, are mounted vertically and they will be in compression. 2 gauges, 2 and 4, are mounted horizontally, which gives force in the other two directions. We cannot mount all of the gauges vertically because the Wheatstone bridge circuits require two resistances to increase and two to decrease when we have 4 active arms. If we mounted 4 gauges the same way, they will not have any difference. All 4 would have the same change, and we won't have any useful reading. This slide shows how the strain gauge resistances will change with a compressive load. R1 and R3 are in compression, and the resistances will be R minus delta R. R2 and R3 will be in tension, and the amount of tension is based on Poisson's ratio, so we multiply delta R by mu. R2 and R4 are equal to R plus mu times delta R. We start with the original equation for the output voltage V0. We substitute in the expressions for R1, R2, R3, and R4 from the previous slide. We do some algebra and assume that 2 times R is much bigger than delta R plus mu times delta R. After doing this, we get a good approximation of the Wheatstone bridge circuit output voltage for an actually loaded beam with a Poisson arrangement to equal the supply voltage times 1 plus mu times the strain times the gauge factor divided by 2. The thing to note is that by adding strain gauges 2 and 4 in the horizontal direction, the output voltage is mu times Vs times the strain times the gauge factor divided by 2, which is larger than if you only used the 2 gauges 1 and 3. The increase in voltage output is roughly 25 to 33% more if the link is made with either aluminum or steel. The mu values for steel are between 0.25 and 0.3. Mu for aluminum is around 0.33. This slide shows how a cantilever beam load cell is built using 4 active arms. Strain gauges 1 and 3 are mounted on the bottom, and strain gauges 2 and 4 are mounted on the top. The process is the same, and the result is the same equation that we get for a full bridge Wheatstone circuit. To summarize this lecture, Wheatstone bridge is used to measure small resistance change, delta R. The resistance change is converted to voltage change by the Wheatstone bridge as input to data acquisition units such as PDAC55. The voltage change is used to find the strain, epsilon. Multiple configurations should be considered, such as number of active arms, mountings, etc., and choose the correct relations based on the configurations is very necessary. The gauge mounting is critical in order to get useful readings out of the circuit. This brings to the end of Lecture 17, Section 2 video. Please write down any questions you have and bring them in